All right, so today we're going to talk about 5.2 definite integrals, and this is going to be a shorter video when compared to the previous video in section 5.1. That was a hour-long video. This one's not going to be as long, but the idea is still going to carry over from the previous video, which is we're going to be finding area under the curve, okay? So I have a simple example here, and what I want us to start to think about is when we're finding area under the curve, there's a difference between total area and then net area, okay? And then that's going to lead us into what we call the definite integral, okay? So what I'd like to do is just, let's start off with the first question, which is find the total area. Or let me just put finding area under the curve from x equals 0 to x equals 4, okay? So what's nice about this is we don't have to rely on the Riemann summariting thing for this problem, because if you look at the shape that we've created from 0 to 4, all right, that's just a right triangle. So we know the area is going to equal 1/2 base times the height. So my base is going to equal 4 because we're starting at x equals 0 and we're going to 4. And then the height is going to be the tippy top point of my right triangle, which is going to be a 4. So we have area equals 1/2 times 4 times 4, which is going to be 16 over 2, or just simply 8. Okay, so we're going to call this region 1. Now, with region 2, we're going to do this problem. Directions are going to be the same. Find the area under the curve from x equals 4 to x equals 8. So let me get out a different color here. So that's going to be this example right here. So from 4 to 8. Okay, and that's going to be this region 2. That right triangle right there. So the idea is still the same. It's a right triangle, so we can use our area formula. However, this one's going to be a little bit different, because we know that the base goes from x equals 4 to x equals 8. So here's my base, which is still equal to 4. However, my height is below the x-axis now. And it goes from y equals 0 to y equals negative 4. So this is going to be negative 4. So my area for this is going to be negative 16 over 2, or negative 8. Now, do not think of this as being negative as like being like going down, or I don't want to say going down. It all goes back to the way I think about this with velocity and acceleration. Do you know what I mean? Like, if you have a negative velocity, that doesn't mean your object is slowing down. It means it's moving in the opposite direction of which you deemed the positive direction. Well, this is going to be the same here. Just because the area has this negative sign right there doesn't mean that this area is shrinking. What it means is this area is below the x-axis, okay? Now, in this section, when we start talking about definite integrals, I might give you this problem right here that says, find the total area from x equals 0 to x equals 8. Now, the total area under the curve would be region 1 plus region 2, but we need to be careful, because if I'm asking for the total area, what I want to know is what is the area underneath both regions and add them up. Now, since this second region has a negative sign in front of it, to guarantee that we have the total area, we just take the absolute value of each of them. So we get a total of 16, okay? However, and this is what we're leading into now, if I wanted you to find the net area, from x equals 0 to x equals 8, well, the net area is going to be, it's still going to be the addition of region 1 and 2, but we don't want the absolute value of either. So we just say that the net area is going to be 8 plus negative 8, which equals 0. Okay? And that leads us into the definition of what a definite integral does. Okay? Because in section 1, we'll go back to section 1 real quick. Go back to this example. Hopefully you remember this example from the other video. In this example, notice that the area under the curve that we're really interested in, it's under the curve, but more importantly, it's above the x-axis. Same thing if we just draw more rectangles. It's the same idea. Even if I went back to the drawing I made earlier here, okay, notice the area is still underneath the curve, but it's above the x-axis. The question becomes, what if I have a curve that looks like this, where you have this area and this area, and you want to find the integral of this? Now, I'm going to use that word a lot more now that we're getting into this thing, which is called integrals, okay? So let me go ahead and give you a definition of what the integral is. Okay, so here's our definition right here. So, a function f defined on the closed interval from a to b is integrable on the closed interval a to b if the limit as delta goes to 0 of the summation from k equals 1 to n of f of k, or f of x sub k star times delta xk exists, and is unique over all partitions from a to b, and all choices of a sub k star are on a partition. This limit is the definite integral of the form a to b, which we will write the integral. Now that's this symbol right here. That's that weird looking s. All right, that's called the integral from a to b of f of x dx is equal to, and then we have the definition on the right hand side. So let me explain to you what this definition on the right hand side means, because you already know what that is. All right, so real quick, in the previous lecture, we looked at a very simple example where we were doing rectangles. Let's cut it. We'll make n equals 2. And we looked at, let's say, right-handed rectangles of this. Okay? And we knew we got this over approximation, but we were just trying to estimate the area underneath the curve. Okay? Now, this right here, f of xk star, is going to be the representative, we call it slice, within one of these rectangles that we're concerned with. It just so happens that since this is hitting the right side, that is the height of the function of that specific rectangle. All right? Now, delta xk is going to be the width of each rectangle that you decide to draw. Now, here we have 2 rectangles. But what this first part is saying here, and I'm going to highlight exactly what I'm talking about. What this is saying is, why don't we just add an infinite amount of rectangles. So the summation says, well, k equals 1 to n, so 1 rectangle or 2 rectangles or 3 rectangles and 4 rectangles and so forth. And if we keep increasing the amount of rectangles we have, then this change in x, the width of those rectangles, eventually is going to approach 0. And that can be, we can see what that looks like with our example that we have here. Now notice I only have 4 rectangles here. If I just let this keep going, that delta x is going to get smaller and smaller and smaller. In fact, I mean, as soon as, you know what, let me change this here a little bit. Maybe 1,000's too much. Let's use, we'll go to 50. But you can see on the right-hand side as n gets larger, in other words, as the number of rectangles increases, the width of each rectangle is getting smaller and smaller and smaller until you have basically an infinite amount of them. So this concept of the limit comes back in full force when we talk about the integral, okay? So now what we're going to do is we're just going to go back to the definition here. So all this is really saying here is that you are creating an infinite amount of rectangles where the width is getting infinitely smaller, and you are just adding up the area of every single one of these rectangles because you got the height and you got the length. And we know area of a rectangle is length times height, or height times length, or side times side. So to kind of abbreviate this crazy looking, and you can see me circling it, to kind of abbreviate this crazy looking, excuse me, definition, what we say is the integral from a to b of f of x dx, where this is called the lower limit. The letter a is called our lower limit. Letter b is called the upper limit. In our example above, if this is x equals 0 and this is x equals 4, then let me write that cleaner. Then my lower limit would be 0, my upper limit would be 4. F of x is going to be the function itself. Since my function is x squared, I replace it with x squared. And then this dx is going to be the distance or the change from all these rectangles where they get infinitely smaller. So we just write dx because we know we need a height and we need a width. And that is going to give us the integral. Okay, now I'm going to teach you different rules on how we do this. Okay, it's called the antiderivative. All right, and I'm going to go over that in the next video next week in section 5.3. Okay, the only thing that I really want us to be able to do right now is just to interpret the different meanings between the total area and then the net area. Definite integrals give us net areas. So they'll tell us, it'll get whatever answer you arrive at will have the net area, because sometimes the area is above the curve and sometimes it's below. I'm sorry, let me say it this way. Sometimes the area is above the x-axis and other times it's below the x-axis. All right, but it's going to give us the net area. If we wanted to find the total area, what we would have to do is break apart our function and then just find each individual region and total them together. Just to reiterate, if we go back to this example all the way up here that I started with at the beginning of class, the net area we found to be 0, and that's because region 1 equaled 8 for its area, and region 2 equaled -8. So our net area is, and this is honestly what it is. The net area is the integral from 0 to 8 of f of x dx. Now, I didn't tell you what the equation of this line is. I mean, you could figure that out on your own. But the area from 0 to 8 of the definite integral f of x dx is going to equal 0 here. However, if I wanted the total area, then what I would have to do is find the area from 0 to 4 of f of x dx, and then add the area from 4 to 8 of f of x dx. I would come up with values for that, and I would take the absolute value of each of them. So we'll call it region, the absolute value of region 1 plus the absolute value of region 2. Okay, which we found to be 16. Okay? So there is a little bit of a difference there between net area and total area. Whenever you're asked to find a definite integral, you are finding net area. In 5.3, and then I think it's 5.5. 5.3 and 5.4 go together. It's just, I just named it as 5.3 because you're doing the same thing over and over again. But honestly, all you got to do right now is just understand the difference between net area and total area. I think the homework has like 3 questions. It's very small. I did that on purpose because chapter 3 and chapter 4 are definitely difficult chapters. There's a lot of work and a lot of theory involved. So what I wanted to do for the week before finals is kind of just give you a nice, easy week. Okay. Next week we're gonna learn these properties. We're gonna learn the power rule for the antiderivative, and we're gonna learn about U substitution, and that's gonna help us to find areas underneath all different types of curves. And also in the next week, I will also nail down the idea between the derivative and the antiderivative are nothing more than just inverse relationships. So hopefully you can see that by now, but if not, you'll definitely see that next week. Your book introduces it kind of early, without really demonstrating how it works, and then they finally hit it in 5.3. So I'm just gonna wait till 5.3 to show you that. Okay, so enjoy the rest of your week, and I will see you in the next video. Bye.